Right now, as you're watching this video, the universe is maintaining a delicate imbalance that makes your existence possible. Every atom in your body, every star in the sky, and every galaxy stretching across the cosmic web exists because perfect symmetry failed catastrophically in the first fraction of a second after the Big Bang. We've been taught to think of symmetry as beautiful, as ideal, as the natural state of things. Perfect mirror images, flawless balance, mathematical elegance. These concepts feel fundamentally correct to our human intuition. But here's what makes this disturbing. If the universe had achieved perfect symmetry, if everything had remained in flawless balance as physics initially predicted, nothing would exist. No stars, no planets, no life. Just empty space filled with perfectly balanced energy, forever. For over a century, physicists assumed that nature preferred symmetry. They built elegant theories around this assumption, created beautiful mathematical frameworks that described a perfectly balanced cosmos. The equations were stunning, the symmetries were profound, and they were completely wrong about reality. In the 1950s, scientists made a discovery so shocking that it forced them to abandon their most cherished beliefs about how the universe works. They found that nature actively violates its own symmetries, breaks its own rules, and does so in ways that seem almost intentionally designed to create complexity and life. This isn't just an abstract physics problem. The asymmetries that physicists have discovered reach into every corner of existence. Your left hand is different from your right hand because of asymmetries in particle physics that occurred 13.8 billion years ago. The reason you can remember the past but not the future stems from the same cosmic imbalances that created matter instead of antimatter. The spiral of your DNA, the beating of your heart, even the thoughts processing in your brain right now, all of these depend on the universe's fundamental inability to achieve perfect balance. Tonight, we're diving deep into one of the most profound questions in all of science. Why perfect symmetry is impossible, and why its absence is the most important fact about reality. We'll discover how tiny violations of symmetry in the first moments after the Big Bang created everything we see today. We'll explore the shocking ways that nature actively chooses chaos over order, imbalance over balance, and complexity over simplicity. And we'll uncover the disturbing possibility that consciousness itself might be the universe's ultimate asymmetry, a cosmic accident that allows matter to observe itself. 3 revelations await you on this journey that will forever change how you see reality. First, you will discover that the matter making up your body shouldn't exist. There should be equal amounts of matter, and antimatter in the universe, perfectly balanced and mutually annihilating, leaving behind only energy and empty space. The fact that you exist means something went catastrophically wrong with perfect balance at the very beginning of time. Second, you'll learn that every process you think of as natural, from the flow of time to the formation of galaxies to the evolution of life, actually depends on mathematical impossibilities. The universe appears to violate fundamental theorems that should make complex structures impossible. We exist in a cosmos that systematically breaks the very rules that govern its own behavior. Third, and most unsettling of all, you'll realize that consciousness might be the universe's way of ensuring that perfect symmetry can never be achieved. Your ability to observe and measure reality might be what prevents the cosmos from collapsing back into perfect, lifeless balance. You're not just witnessing the universe's asymmetries. You might be actively creating them through the simple act of being aware. The story we're about to tell unfolds across scales from the quantum to the cosmic, from the first microsecond of time to the heat death of everything. It's a story that reveals why perfection is not just unachievable, it's actually terrifying. Perfect symmetry would be perfect death, a universe frozen in mathematical beauty, but devoid of any possibility for change, growth, or experience. This investigation will take us from the particle accelerators where scientists, shatter matter to glimpse the fundamental asymmetries of nature, to the cosmic microwave background radiation that preserves the memory of the universe's first asymmetrical moment, to the twisted molecules of life that could never exist in a perfectly symmetrical world. We'll explore why every attempt to create perfect balance in nature fails, why the equations of physics themselves seem designed to generate chaos, and why the most beautiful theories in science predict a universe that looks nothing like the one we actually inhabit. If you're fascinated by the hidden rules that govern reality and want to understand why existence itself is a cosmic accident, subscribe and hit the thumbs up button. And here's a question that might keep you awake tonight. If perfect symmetry is impossible, what does that tell us about the nature of perfection itself? Comment below with your thoughts. I'll pen the most mind-bending response. The rabbit hole we're about to descend has no bottom. Every answer we uncover leads to 3 more questions, each more disturbing than the last. But somewhere in this maze of broken symmetries and impossible balances lies the deepest truth about why anything exists at all. As we begin this journey, remember that you're not just learning about the universe's asymmetries, you're experiencing them. The electrical impulses firing in your brain as you process these words, the biochemical reactions sustaining your life as you watch, the quantum processes maintaining the integrity of your thoughts. All of these depend on the fundamental fact that perfect balance is a beautiful impossibility. Now let's begin our exploration of why the universe cannot be perfectly symmetrical, and why that impossibility might be the most important truth you'll ever encounter. Chapter 1. Broken Mirror. The story of cosmic asymmetry begins with the most shocking discovery in the history of physics. A discovery so counterintuitive that the scientists who made it initially refused to believe their own results. In 1956, 3 Chinese-American physicists named Chen-Ning Yang, Sung-Dao Lee, and Chen-Xiang Wu designed an experiment that would shatter humanity's oldest assumption about the nature of reality. For thousands of years, humans believed that the universe possessed perfect mirror symmetry. Just as your reflection in a mirror appears identical but reversed, physicists assumed that all natural processes would look the same if you flipped them left to right in a cosmic mirror. This principle, called parity conservation, wasn't just a theory. It was considered a fundamental law of nature, as unbreakable as the conservation of energy or the constancy of the speed of light. The elegance of parity conservation made intuitive sense. If you filmed a spinning planet and then played the footage backwards through a mirror, the laws of physics should remain unchanged. If you watched an atomic nucleus decay in normal space and then observed its mirror image, the process should unfold identically. The mathematics was beautiful, the symmetry was profound, and the assumption had guided physics for decades without a single violation. Chen-Ning Yang and Sung-Dao Lee began questioning this foundational principle when they encountered puzzling results in particle physics experiments. Certain particles seemed to behave differently than parity conservation predicted, but the violations were so subtle that most physicists dismissed them as experimental errors. Yang and Lee took a different approach. They decided to test whether parity conservation was actually true. Working with Chen-Xiang Wu, they designed an experiment using cobalt-60 nuclei cooled to near absolute zero and placed in a powerful magnetic field. The setup was devilishly simple. If parity conservation held true, the radioactive cobalt nuclei should emit electrons randomly in all directions. But if parity conservation was violated, the electrons would show a preferred direction. They would be emitted, preferentially along or against the direction of the nucleus spin. On January 15, 1957, Wu announced results that sent shockwaves through the scientific community. The cobalt nuclei were violating parity conservation. The electrons weren't being emitted randomly. They showed a clear directional preference. The universe had a built-in handedness, a fundamental asymmetry that distinguished left from right at the most basic level of reality. The implications were staggering. If you could somehow flip the entire universe through a cosmic mirror, the laws of physics would change. Nuclear processes would unfold differently. Particle interactions would follow altered patterns. The mirror universe would be genuinely different from our own, governed by subtly modified natural laws. But the story gets even stranger. Wu's experiment didn't just reveal that parity conservation was violated. It showed that the violation was maximal for certain particles. Neutrinos, the ghostly particles that barely interact with matter, turned out to be exclusively left-handed. There are no right-handed neutrinos in nature, despite the fact that the equations of physics allow for both possibilities. To put this in perspective, imagine discovering that every screw in the universe naturally turns left, that every whirlpool spins counterclockwise, that every human being is born left-handed. This is the level of cosmic asymmetry that Wu's experiment revealed. Nature doesn't just slightly prefer one-handedness over another. For certain fundamental particles, it exclusively chooses one orientation and completely forbids the other. The discovery earned Yang and Li the Nobel Prize in Physics in 1957, just 1 year after their initial proposal. But for Wu, whose experimental genius made the discovery possible, recognition came much later. The scientific establishment wasn't ready to accept that a fundamental symmetry of nature could be so completely and dramatically violated. As news of the parity violation spread through the physics community, scientists began to realize that their entire understanding of natural symmetry needed to be rebuilt from the ground up. The universe wasn't just imperfectly symmetrical. It was actively asymmetrical, systematically breaking symmetries that should have been preserved. This revelation opened up a cascade of questions that continue to drive physics research today. If parity can be violated, what other symmetries might be broken? If the universe has a preferred handedness, what does that tell us about the fundamental structure of space-time? And most disturbing of all, if perfect symmetry is impossible at the quantum level, what does that mean for our understanding of perfection itself? The broken mirror of parity conservation became the first crack in humanity's assumption that nature prefers balance and elegance. As we'll discover in the chapters ahead, this crack has widened into a chasm that encompasses every level of reality from the quantum to the cosmic. The universe doesn't just tolerate asymmetry, it requires it, demands it, and builds complexity through the systematic violation of its own most beautiful symmetries. Whose cobalt nuclei, spinning in their magnetic field and emitting electrons preferentially to the left, became the first clear evidence that the cosmos is fundamentally lopsided. But as shocking as this discovery was, it represented only the beginning of our understanding of cosmic asymmetry. The true depths of the universe's broken symmetries would take decades more to fully appreciate. What Wu couldn't have known in 1957 was that she had uncovered the first thread of a tapestry of asymmetries that extends from the subatomic to the galactic scale. The left-handed neutrinos in her experiment were connected to the matter-antimatter imbalance that created every atom in existence, to the arrow of time that gives direction to causality to the formation of the first stars and galaxies in the early universe. The mirror was broken, and through that first crack, humanity glimpsed a cosmos far stranger and more beautiful than perfect symmetry could ever provide. But to understand why this asymmetry is not just interesting but absolutely essential, we need to dive deeper into the quantum realm where the fundamental forces of nature reveal their true character. Chapter 2. Quantum Rebellion in the Basement of CERN. Buried 100 meters beneath the Swiss-French border, machines accelerate particles to 99.9999991%, the speed of light, and smash them together with energies that recreate conditions from the first moments after the Big Bang. These collisions generate exotic particles that exist for billionths of a second before decaying into cascades of daughter particles. And in these fleeting moments of existence, we witness the quantum realm's systematic rebellion against perfect symmetry. The standard model of particle physics, our most successful theory of fundamental reality, describes a universe built from seemingly symmetrical components. For every type of matter particle, there should exist a corresponding antimatter particle with identical mass but opposite charge. Electrons have positrons, protons have antiprotons, neutrons have antineutrons. The mathematics suggests that matter and antimatter should be created in perfectly equal amounts, annihilating each other completely whenever they meet. This symmetrical picture creates what cosmologists call the antimatter problem, one of the most profound puzzles in modern physics. If the Big Bang created equal amounts of matter and antimatter, as the equations predict it should have, then every particle should have eventually encountered its antiparticle counterpart. The result would be complete mutual annihilation, leaving behind a universe filled with nothing but photons of light racing through empty space. Yet here you are, made of matter, watching this video on a device made of matter, living on a planet made of matter, orbiting a star made of matter. The observable universe contains approximately YY particles of matter and virtually no antimatter. This represents such a dramatic violation of expected symmetry that it shouldn't be possible according to our most fundamental theories. The solution to this puzzle lies in subtle asymmetries in how matter and antimatter behave. Asymmetries so small they can only be detected in the most sophisticated particle physics experiments, yet so crucial that they make the existence of everything possible. These asymmetries violate what physicists call CP symmetry, a combination of charge conjugation C and parity P that should make matter and antimatter behave as perfect mirror images of each other. In 1964, physicists James Cronin and Val Fitch made a discovery that would earn them the Nobel Prize and revolutionize our understanding of cosmic asymmetry. Working with neutral kaons, particles that can spontaneously transform between matter and antimatter states, they found that the transformation wasn't perfectly symmetrical. Kaons had a slight tendency to transform from antimatter to matter more often than from matter to antimatter. The asymmetry was incredibly tiny, only about 1 part in 1,000. But this minuscule violation of CP symmetry had monumental implications. It meant that in the hot, dense environment of the early universe, matter-antimatter pairs wouldn't always annihilate perfectly. For every billion antimatter particles that found a matter particle to annihilate with, one matter particle would be left behind without a partner. To put this in perspective, imagine a cosmic dance where billions of couples perform perfect synchronized movements before vanishing in flashes of light. But occasionally, through some subtle difference in the choreography, one dancer is left standing alone when the music stops. After billions upon billions of these dances, enough lone dancers accumulate to build galaxies, stars, planets, and eventually, beings capable of wondering why they exist at all. The quantum mechanical origins of CP violation are even more mysterious than the phenomenon itself. The violation appears to be connected to the complex phases of quantum wave functions, mathematical quantities that have no direct physical analog, but somehow encode the universe's preference for matter over antimatter. These phases are like hidden rotations in an abstract mathematical space, invisible to direct observation, but crucial for determining the outcomes of particle interactions. More recent experiments at facilities like the LHCb detector at CERN have revealed that CP violation extends far beyond neutral kaons. B mesons, particles containing bottom quarks, show even larger asymmetries between matter and antimatter behavior. D mesons, containing charm quarks, exhibit their own unique violations. Each new discovery reveals that the quantum rebellion against perfect symmetry is not an isolated phenomenon but a fundamental characteristic of reality. The Standard Model attempts to explain these asymmetries through a mechanism called the CKM matrix, named after physicists Kababo, Kobayashi, and Maskawa. This mathematical framework describes how quarks can change from one type to another, and it includes complex phases that generate CP violation. But even this sophisticated theory struggles to explain why the violations are large enough to account for the universe as matter content. Some physicists suspect that additional sources of CP violation exist beyond those described by the Standard Model. These hypothetical violations might have operated in the first fraction of a second after the Big Bang, when the universe was hot enough for exotic particles to exist and interact in ways that are impossible to recreate in earthly laboratories. The search for these additional symmetry violations drives some of the most ambitious experiments in modern physics. The Tokai to Kamioka T2K experiment in Japan shoots beams of neutrinos 295 kilometers underground to detect subtle differences in how neutrinos and antineutrinos oscillate between different types. The results suggest that neutrinos, too, might violate CP symmetry in ways that could help explain the cosmic matter-antimatter imbalance. But perhaps the most unsettling aspect of quantum asymmetry is how it challenges our intuitive understanding of cause and effect. In the quantum realm, particles exist in superpositions of multiple states until they're observed or interact with their environment. The act of measurement doesn't just reveal pre-existing properties, it actually creates them through the collapse of the wave function. This means that the asymmetries we observe in particle physics experiments might not be fixed properties of particles themselves, but rather emergent phenomena that arise from the interaction between quantum systems and their environment. The universe's preference for matter over antimatter might be constantly recreated through countless quantum measurements and interactions, rather than being determined once and for all in the early universe. Consider the implications. Every time a detector registers a particle decay, every time a cosmic ray interacts with Earth's atmosphere, every time quantum decoherence occurs in any system anywhere in the universe, the asymmetries that make existence possible are being reinforced and regenerated. Reality's lopsidedness isn't a historical accident. It is an ongoing quantum rebellion that must be constantly maintained. The quantum realm, a systematic violation of symmetry, reveals that perfect balance isn't just unlikely. It is actively prevented by the fundamental laws of physics. At the deepest level of reality, nature appears to be programmed to create imbalance, to generate the asymmetries upon which all complexity depends. Chapter 3. Cosmic Genesis. 3 minutes and 17 seconds after the Big Bang, the universe faced its first existential crisis. The temperature had dropped to a mere billion degrees Kelvin, cool enough for protons and neutrons to form atomic nuclei for the first time. But something was catastrophically wrong with the cosmic inventory. According to the Standard Model of particle physics, the universe should have contained exactly equal amounts of matter and antimatter at this point. What actually existed was a cosmos filled almost entirely with matter, with antimatter representing less than 1 part in a billion of the total mass energy content. This asymmetry represents the most important 3 minutes in cosmic history, a period so crucial that if it had unfolded even slightly differently, the universe would be an empty void of photons racing through space-time with no possibility of ever forming stars, planets, or life. The matter-antimatter imbalance that emerged during these moments wasn't just a minor deviation from theoretical predictions. It was a violation of fundamental symmetries so severe that it challenges our understanding of why anything exists at all. To appreciate the magnitude of this cosmic genesis, consider what should have happened according to our best theories. In the first fraction of a second after the Big Bang, the universe was a seething cauldron of energy, hot enough to spontaneously create matter-antimatter particle pairs from pure radiation. As the cosmos expanded and cooled, these particle pairs should have annihilated each other completely, converting all matter back into photons and leaving behind a perfectly empty, perfectly symmetrical universe. The fact that this annihilation wasn't complete indicates that something extraordinary happened during a period cosmologists call baryogenesis, the generation of the matter asymmetry. Three conditions must be satisfied for baryogenesis to occur, as outlined by Russian physicist Andrei Sakharov in 1967. First, there must be processes that violate baryon number conservation, allowing the creation of more matter particles than antimatter particles. Second, these processes must violate CP symmetry, ensuring that matter and antimatter don't behave identically. Third, the universe must be out of thermal equilibrium, preventing the asymmetry from being erased by reverse reactions. The early universe satisfied all three Sakharov conditions, but only during a narrow window of time when exotic physical processes could operate. As the cosmos expanded and cooled, phase transitions occurred that fundamentally altered the laws of physics. Fields that had been perfectly symmetrical suddenly acquired non-zero values, breaking symmetries and creating the conditions necessary for matter generation. One of the most promising mechanisms for baryogenesis involves the hypothetical decay of particles called leptoquarks during the universe's first microsecond. These exotic particles, which exist only at extremely high energies, can transform quarks into leptons and vice versa. If leptoquarks decay asymmetrically, preferentially producing matter over antimatter, they could generate the observed cosmic imbalance. But here's where the story becomes even more extraordinary. The amount of asymmetry required to explain the current matter content of the universe is incredibly specific. If the violation of matter-antimatter symmetry had been even slightly smaller, insufficient matter would have survived the annihilation epoch to form the first hydrogen nuclei. If the violation had been larger, the universe would have been so dense with matter that it would have collapsed back into a black hole before stars could form. The precision required for successful baryogenesis reveals what cosmologists call the Goldilocks problem of cosmic asymmetry. The violation of CP symmetry must be not too large, not too small, but exactly right to create a universe capable of developing complex structures. This fine-tuning is so extreme that some physicists argue it represents evidence for multiple universes. The idea that we exist in the one cosmic lottery ticket that happened to draw winning numbers. Recent observations of the cosmic microwave background radiation by the Planck satellite have provided unprecedented precision in measuring the universe as matter content. The data reveals that ordinary matter comprises exactly 4.9% of the total cosmic energy density. This seemingly small percentage represents an enormous victory for matter over antimatter, a victory that required violations of fundamental symmetries, operating with clockwork precision during the first moments of cosmic existence. The cosmic microwave background also preserves fossil evidence of the universe's first asymmetrical structures. Tiny fluctuations in temperature across the sky, measuring only a few millionths of a degree, represent the seeds from which all cosmic structure would eventually grow. These fluctuations themselves violate perfect symmetry. They create a pattern of hot and cold spots that breaks the universe as rotational and translational symmetry. Without these primordial asymmetries, gravity would have had nothing to work with. Matter would have remained perfectly spread throughout space, never clumping together to form the first stars. The cosmic web of galaxies, filaments, and voids that characterizes today's universe traces its origins directly to these microscopic violations of perfect homogeneity. In the cosmic microwave background, the formation of the first stars around 100 million years after the Big Bang represents another crucial asymmetry in cosmic evolution. These stellar furnaces did not ignite uniformly throughout space. They formed preferentially in regions where dark matter had begun to clump under its own gravity. The locations of the first stars were determined by quantum fluctuations that have been stretched to cosmic scales by cosmic inflation, creating an intricate pattern of matter over densities and underdensities. When these first stars exhausted their nuclear fuel and exploded as supernovas, they scattered heavy elements throughout space in dramatically asymmetrical patterns. The shock waves from these explosions triggered the formation of subsequent generations of stars, creating feedback loops that amplified small asymmetries into large-scale cosmic structures. The element carbon, essential for all known forms of life, was forged in the cores of dying stars and distributed through space in highly irregular patterns that would ultimately determine where planets capable of supporting biology could form. The cosmic genesis of asymmetry thus extends far beyond the first few minutes after the Big Bang. Each epoch of cosmic evolution has built upon the asymmetries established by earlier epochs, creating an ever more complex hierarchy of broken symmetries. From the matter-antimatter imbalance to the cosmic web to stellar nucleosynthesis, the universe has systematically amplified tiny deviations from perfect balance into the rich tapestry of structures we observe today. Perhaps most remarkably, the cosmic genesis of asymmetry appears to be an ongoing process. Dark energy, the mysterious force driving the universe's accelerating expansion, is creating new asymmetries by stretching space itself. Regions of the universe are being carried apart faster than light can travel between them, breaking the causal symmetry that once connected all parts of the cosmos. Future observations with next-generation telescopes like the James Webb Space Telescope and the extremely large telescope will probe even deeper into cosmic history, potentially revealing additional sources of primordial asymmetry that shaped the universe's evolution. Each new discovery adds another layer to our understanding of how the cosmos systematically violates its own symmetries in service of creating complexity and structure. The 3 minutes and 17 seconds of Big Bang nucleosynthesis thus represent more than just a historical curiosity. They mark the moment when the universe committed itself to asymmetry, when perfect balance was abandoned forever in favor of the lopsided reality that makes existence possible. This cosmic genesis continues to unfold around us, creating new asymmetries and new possibilities with each passing moment. Chapter 4. Temporal Arrow. Right now, as you watch this video, you re-experiencing the universe as most mysterious asymmetry, one so fundamental that it shapes every moment of your existence, yet so familiar that you never question its reality. You remember yesterday, but not tomorrow. You can affect the future, but not the past. Milk mixes into coffee, but never spontaneously unmixes. Glass shatters, but never spontaneously reassembles. You age relentlessly forward through time, never backward. This directional flow of time, what physicists call the arrow of time, represents one of the deepest puzzles in all of science. The fundamental laws of physics are almost entirely time reversible. If you filmed most physical processes and played the footage backward, the reverse process would still obey the same physical laws. Yet the universe you experience has a clear temporal direction, an unmistakable asymmetry between past and future that appears to violate the time-symmetrical nature of underlying physics. The mystery deepens when you consider that the equations describing electromagnetic fields, gravity, quantum mechanics, and even nuclear forces work equally well whether time moves forward or backward. Einstein's theory of relativity treats time as just another dimension of spacetime with no inherent directionality. Schrodinger's equation, the foundation of quantum mechanics, is perfectly time reversible. If the fundamental laws are symmetric in time, where does the arrow of time come from? The answer lies in a concept that bridges the microscopic and macroscopic worlds: entropy. In 1877, Austrian physicist Ludwig Boltzmann proposed that the arrow of time emerges from the statistical behavior of enormous numbers of particles. When you pour milk into coffee, billions of milk molecules spread throughout the liquid, moving from an organized state, milk separated from coffee, to a disorganized state, milk mixed throughout coffee. The probability of this process spontaneously reversing, of all the milk molecules simultaneously moving back to one corner of the cup, is so astronomically small that it effectively never happens. But Boltzmann's statistical explanation immediately raises an even deeper question. If entropy always increases, why was the universe ever in a low entropy state to begin with? The second law of thermodynamics tells us that isolated systems always evolve toward maximum entropy, toward perfect thermal equilibrium, where no further change is possible. If this law has always operated, the universe should already be in maximum entropy, a heat-death state where no asymmetries exist and no processes can occur. The fact that you exist in a universe capable of change and evolution means that the cosmos began an extraordinarily special state of extremely low entropy. The Big Bang wasn't just an explosion of matter and energy. It was an explosion of organization, a cosmic event that created vast amounts of extractable work and free energy. Every star that shines, every chemical reaction that occurs, every thought that forms in your brain is powered by the gradual dissipation of this primordial organization. To put the improbability of the universe's initial low-entropy state in perspective, consider that there are roughly 10,120 different ways to arrange the matter and energy in the observable universe. Of these possibilities, only an infinitesimally small fraction correspond to states of low entropy capable of evolving into complex structures like galaxies, stars, and life. The probability that the universe would randomly begin in such a special state is so small that it dwarfs the probability of any other event we can imagine. This realization led cosmologist Roger Penrose to calculate what he calls the Creator's aim, the precision with which the initial conditions of the universe must have been selected to produce the arrow of time we observe. The cosmic microwave background radiation provides direct evidence for the universe's initial low-entropy state. This ancient light, released 380,000 years after the Big Bang when the cosmos first became transparent, shows remarkable uniformity across the sky. The temperature variations are only about 100 microkelvin, tiny fluctuations that represent quantum mechanical uncertainties stretched to cosmic scales by inflation. These minute temperature variations in the cosmic microwave background represent the seeds of all future cosmic asymmetry. Regions that were slightly denser than average would grow under gravitational attraction, eventually forming the first stars and galaxies. Regions that were slightly less dense would become cosmic voids. The entire large-scale structure of the universe, the cosmic web of galaxies separated by vast empty spaces, traces its origins to these primordial asymmetries preserved in the afterglow of creation. But the arrow of time reveals an even stranger feature of cosmic evolution: information irreversibility. When you burn a book, the information contained in its pages isn't destroyed. Is scrambled into the microscopic details of smoke particles, ash molecules, and photons of heat radiation. In principle, if you could track every particle produced by the burning and reverse their motions with perfect precision, you could reconstruct the original book. The information is preserved, but becomes practically inaccessible. This distinction between theoretical and practical irreversibility underlies much of what we experience as the arrow of time. Your memories form because neural connections in your brain create lasting physical changes that encode information about past events. These changes are thermodynamically irreversible. The energy cost of perfectly erasing a memory and returning the brain to its exact previous state would be enormous. Your consciousness exists because your brain constantly creates irreversible records of its own states. The formation of black holes represents an extreme case of information irreversibility that has puzzled physicists for decades. When matter falls into a black hole, it appears to disappear permanently from the observable universe. But according to quantum mechanics, information cannot be destroyed. It can only be scrambled or hidden. This creates the black hole information paradox. What happens to the information content of objects that cross a black hole's event horizon? Stephen Hawking's discovery that black holes emit radiation through quantum mechanical processes suggested a possible resolution. Hawking radiation carries away energy from black holes, causing them to slowly evaporate. If this radiation somehow encodes the information that originally fell into the black hole, then information conservation could be preserved. But the encoding mechanism remains mysterious, requiring quantum mechanical processes that operate across vast scales of space and time. Recent developments in quantum gravity research have revealed deep connections between the arrow of time and the fundamental structure of spacetime itself. Some theories propose that time's directional nature emerges from the quantum mechanical entanglement between different regions of the universe. As the cosmos evolves, quantum entanglement becomes increasingly complex, creating an asymmetrical structure in the quantum information that defines reality. These discoveries suggest that the arrow of time isn't just an emergent property of statistical mechanics. It might be built into the fabric of reality at the most fundamental level. If spacetime itself has a directional structure, then temporal asymmetry becomes a basic feature of existence rather than an accidental byproduct of special initial conditions. The arrow of time also plays a crucial role in biological evolution and the development of complexity. Life is a fundamentally asymmetrical process. Organisms extract low-entropy energy from their environment, food, sunlight, and export high-entropy waste, heat, chemical byproducts. This constant flow of energy allows living systems to maintain and increase their internal organization while contributing to the overall increase in cosmic entropy. Evolution itself depends on temporal asymmetry. Genetic mutations create variations in offspring that are tested by natural selection. Beneficial mutations are preserved and passed to future generations, while harmful mutations are eliminated. This process only works because causation flows from past to future. The fitness consequences of genetic changes can only be evaluated after they occur, not before. The arrow of time thus connects the deepest mysteries of physics to the everyday experiences that define human existence. Every choice you make, every memory you form, every plan you pursue exists because the universe began in an improbable state of low entropy that continues to dissipate through irreversible processes. Time's arrow points toward a future of increasing disorder, but within that cosmic trend, temporary islands of organization and complexity can emerge and flourish. Understanding temporal asymmetry reveals why perfect symmetry would be incompatible with existence as we know it. A time-symmetric universe would have no arrow of time, no distinction between past and future, no possibility for memory, learning, or evolution. Perfect temporal symmetry would create a static cosmos where nothing could ever truly change or develop. Chapter 5. Biological spiral. Deep within every cell of your body, twisted into a double helix that spirals relentlessly in one direction, lies DNA, perhaps the most profound biological asymmetry ever discovered. This molecular staircase doesn't just randomly coil in any direction. Every strand of DNA in every living organism on Earth spirals in the same right-handed direction, creating a universal biological handedness that has persisted for over 3.8 billion years of evolution. This isn't merely an interesting biological quirk. The consistent handedness of DNA represents what biochemists call homochirality, a fundamental asymmetry in the molecular structure of life that extends far beyond genetics into every biochemical process that sustains your existence. The amino acids that build your proteins are exclusively left-handed. The sugars that power your cellular metabolism are exclusively right-handed. Life on Earth has made a cosmic choice for asymmetry that goes against every principle of chemical probability. To understand how extraordinary this biological asymmetry truly is, consider what should happen when organic molecules form spontaneously in nature. In laboratory experiments that recreate the conditions of early Earth, scientists consistently produce equal amounts of left-handed and right-handed molecules, what chemists call a racemic mixture. If you let amino acids form naturally from simpler chemicals, you get 50% left-handed and 50% right-handed versions, perfectly balanced and completely symmetrical. Yet life uses only one-handedness of each type of molecule. Your DNA polymerase enzymes can only read right-handed DNA helices. Your protein synthesis machinery can only assemble left-handed amino acids into functional proteins. Your metabolic enzymes can only process right-handed sugars. If you somehow replaced all the left-handed amino acids in your body with their right-handed counterparts, every protein would become non-functional and you would die instantly. The origin of biological homochirality represents one of the deepest unsolved mysteries in the study of life as emergence. How did the first living systems choose one molecular handedness over another? What process could have broken the perfect left-right symmetry of prebiotic chemistry to create the uniformly chiral world of biology? Some scientists propose that the asymmetry originated from circularly polarized light from space. Certain types of stars and cosmic phenomena produce light waves that spiral preferentially in one direction. When this polarized radiation interacts with organic molecules, it can selectively destroy one-handedness while leaving the other intact. Observations of the Orion Nebula have detected circularly polarized infrared radiation intense enough to create significant chiral asymmetries in organic compounds. Others suggest that the weak nuclear force, which we encountered earlier as the source of parity violation in particle physics, might have played a role in life's chiral selection. Because the weak force distinguishes between left and right at the quantum level, it creates tiny energy differences between mirror image molecules. These differences are incredibly small, only about 1 part in 1017, but they might have been enough to bias the earliest chemical evolution toward one-handedness. Perhaps the most intriguing possibility is that biological chirality represents a frozen accident, a random choice made by the first self-replicating molecules that became locked in place by evolutionary history. Once the earliest RNA molecules happened to adopt one-handedness, any competing molecules with opposite-handedness would be incompatible with the established replication machinery. The initial choice would create a positive feedback loop, with successful chiral molecules producing more copies of themselves, while opposite-handed variants failed to replicate. But homochirality extends far beyond the molecular level into the very architecture of living systems. Your heart sits on the left side of your chest, displaced from the body's central axis in a pattern that's conserved across vertebrate evolution. Your intestines spiral in consistent patterns that optimize nutrient absorption. Even the microscopic cilia that move fluids through your respiratory system beat in coordinated asymmetrical patterns that create directed flow. The asymmetry of biological structures often serves crucial functional purposes that wouldn't be possible in a perfectly symmetrical organism. Consider the spiral shells of nautiluses and snails, which grow in logarithmic patterns to distribute stress evenly while maintaining structural strength. The consistent handedness of these shells, usually right-handed for most species, allows for efficient packing of internal organs and optimal swimming or crawling mechanics. At the cellular level, asymmetry plays essential roles in fundamental biological processes. During cell division, the mitotic spindle that separates chromosomes forms asymmetrical structures that ensure each daughter cell receives the correct genetic material. The failure of these asymmetrical mechanisms leads to aneuploidy, chromosomal abnormalities that can cause cancer or developmental disorders. Even more remarkably, many biological asymmetries appear to be actively maintained by sophisticated molecular machines. The protein complex responsible for left-right patterning during embryonic development, called the node, contains hundreds of rotating cilia that beat in coordinated patterns to create fluid flows that establish the body's asymmetrical axis. Mutations that disrupt this machinery can cause situs inversus, a condition where all internal organs develop on the opposite side of the body. The prevalence of asymmetry in biology raises profound questions about the relationship between structure and function in living systems. Would perfectly symmetrical organisms be possible? Computer simulations suggest that many biological functions require some degree of asymmetry to operate efficiently. Blood circulation systems work best with asymmetrical branching patterns that optimize flow distribution. Neural networks require asymmetrical connection patterns to process information effectively. Recent discoveries in developmental biology have revealed that asymmetry plays a crucial role in the emergence of complex behaviors and cognitive abilities. The human brain shows pronounced left-right asymmetries that correlate with language processing, spatial reasoning, and emotional regulation. These asymmetries begin forming early in fetal development and continue to influence brain function throughout life. The connection between biological asymmetry and consciousness represents one of the most intriguing frontiers in neuroscience. Some researchers propose that the brain's asymmetrical structure might be necessary for the integration of information that gives rise to conscious experience. The left and right hemispheres of your brain process information differently, and the constant communication between these asymmetrical systems might be what creates the unified stream of consciousness you experience. Evolutionary biologists have begun to recognize that asymmetry itself might be subject to natural selection. Organisms with optimal degrees of asymmetry, enough to enable complex functions, but not so much as to create instabilities, would have advantages over both perfectly symmetrical organisms and those with excessive asymmetries. This suggests that evolution doesn't just tolerate biological asymmetry. It actively fine-tunes it to maximize organismal fitness. The study of biological asymmetry has practical implications for understanding disease and developing medical treatments. Many pathological conditions involve the disruption of normal asymmetrical patterns. Cancer cells often show altered chirality in their metabolic processes, which might be exploited to develop targeted therapies. Understanding the molecular basis of biological handedness could lead to new approaches for treating genetic disorders that affect left-right patterning. Perhaps most surprisingly, biological asymmetry extends into the realm of ecological interactions and ecosystem dynamics. Predator-prey relationships often involve asymmetrical adaptations. Prey species develop defenses against specific attack strategies, while predators evolve specialized hunting techniques. These asymmetrical arms races drive the diversification of life forms and the evolution of increasingly complex biological communities. The temporal dynamics of ecosystems also show pronounced asymmetries. Ecological successions follow predictable directional patterns, with pioneer species preparing environments for later successional stages that eventually exclude the pioneers themselves. These asymmetrical processes create the biodiversity patterns we observe in nature, from the regular spacing of trees in forests to the patchy distribution of species across landscapes. Climate change research has revealed that biological asymmetries make ecosystems particularly vulnerable to environmental disruptions. Species with specialized asymmetrical adaptations, like flowers that co-evolved with specific pollinators, or predators adapted to hunt particular prey, may be less resilient to changing conditions than more symmetrical generalist species. The biological spiral of asymmetry thus encompasses everything from the molecular machinery of life to the global patterns of biodiversity. Each level of biological organization has evolved its own characteristic asymmetries, creating a nested hierarchy of broken symmetries that enables the complexity we observe in living systems. Perfect symmetry wouldn't just be unusual in biology. It would be incompatible with life as we know it. Understanding biological asymmetry reveals why the quest for perfect balance in natural systems is fundamentally misguided. Life doesn't seek equilibrium. It creates and maintains dynamic asymmetries that enable growth, reproduction, adaptation, and evolution. The biological world is a testament to the creative power of broken symmetry, a living demonstration that the most beautiful and complex phenomena emerge not from perfect balance, but from the systematic violation of symmetrical principles. Chapter 6. Mathematical Impossibility. In 1872, German mathematician Felix Klein discovered something that would forever change how mathematicians think about symmetry and perfection. While studying the abstract structures that underlie geometric transformations, Klein proved that certain types of perfect symmetry are not just unlikely or improbable, they are mathematically impossible. His work revealed that the universe operates under fundamental constraints that prevent the achievement of absolute symmetrical perfection. Constraints so basic that they apply to everything from subatomic particles to cosmic structures. Klein's insight emerged from his investigation of what mathematicians call group theory, the mathematical framework that describes all possible symmetries. When you rotate a circle, reflect it through any axis, or translate it to any position, you're performing operations that belong to the circle's symmetry group. For simple shapes like circles and spheres, these groups can be infinite, suggesting that perfect symmetry might be achievable in mathematical space. But when Klein extended his analysis to more complex structures, particularly those that exist in spaces with more than 2 dimensions, he encountered fundamental limitations. Certain combinations of symmetrical operations, when applied to objects in 3-dimensional space, lead to mathematical contradictions. The operations themselves are individually valid, but their combinations create impossible scenarios where objects would need to exist in multiple incompatible states simultaneously. Consider the example of a perfect crystal lattice extending infinitely in all directions. Such a structure should exhibit perfect translational symmetry. Every point in the lattice should be identical to every other point when viewed from the appropriate reference frame. But Klein showed that infinite perfect lattice cannot exist in 3-dimensional space because they violate fundamental topological constraints. Any real crystal must have boundaries, defects, or irregularities that break its perfect symmetry. These mathematical impossibilities aren't mere academic curiosities. They have profound implications for the physical world because the mathematics that describes symmetry is the same mathematics that underlies the laws of physics. If perfect symmetry is mathematically impossible in certain contexts, then the physical systems governed by those mathematical relationships cannot achieve perfect symmetry either. The connection between mathematical impossibility and physical reality becomes clear when we examine phase transitions in condensed matter physics. When water freezes into ice, it undergoes a spontaneous symmetry-breaking transition. The liquid water has continuous rotational symmetry. Its properties look the same from any direction. But ice crystals have discrete symmetries, with special axes and preferred orientations that break the continuous symmetry of the liquid phase. What makes this transition mathematically inevitable is a theorem proved by physicist Vitaly Pokrovsky in 1979. Pokrovsky showed that continuous symmetries cannot be maintained in finite temperature systems with local interactions. The thermal fluctuations that exist at any temperature above absolute zero will eventually break any continuous symmetry, forcing the system into a state with discrete symmetries instead. This mathematical constraint explains why you never observe truly perfect crystals in nature. Every ice crystal contains defects, dislocations, grain boundaries, impurities, or surface irregularities that violate perfect crystalline symmetry. These defects aren't accidental imperfections that could be eliminated with better experimental techniques. They're mathematically mandatory features that arise from the fundamental impossibility of maintaining perfect symmetry in finite systems. The mathematical impossibility of perfect symmetry extends into the realm of topology, the branch of mathematics that studies properties preserved under continuous deformations. Topological theorems place strict limits on the types of symmetries that can exist in different dimensional spaces. For example, The hairy ball theorem proves that you cannot comb a hairy sphere flat without creating at least one cowlick, a point where the symmetry of the hair pattern necessarily breaks down. This seemingly whimsical result has serious implications for physics. The hairy ball theorem explains why global weather patterns must contain at least one cyclone or anticyclone at any given time. The Earth's spherical surface creates topological constraints that make perfectly uniform wind patterns impossible. The theorem also applies to magnetic fields, explaining why perfect magnetic field symmetries cannot exist around spherical objects. Another profound mathematical constraint comes from Gödel's incompleteness theorems, which reveal fundamental limitations in any formal system powerful enough to describe basic arithmetic. Gödel proved that such systems must be either incomplete, unable to prove all true statements within their domain, or inconsistent, capable of proving contradictory statements. This creates what mathematicians call the completeness-consistency trade-off. The implications for perfect symmetry are subtle but far-reaching. Any mathematical system sophisticated enough to describe perfect symmetrical relationships must also be sophisticated enough to encounter Gödel's limitations. This means that complete, consistent descriptions of perfect symmetry are mathematically impossible. There will always be true statements about symmetrical relationships that cannot be proven within any given mathematical framework. Recent developments in algebraic topology have revealed even deeper impossibility results. The classification of finite simple groups, a mathematical achievement sometimes called the classification of all possible symmetries, required over 10,000 pages of proofs and revealed that the landscape of possible symmetries has a surprisingly complex and irregular structure. Most remarkably, the classification theorem shows that perfect symmetry groups, those with no normal subgroups other than the trivial ones, become increasingly rare as their complexity increases. Of all possible finite groups, only a vanishingly small fraction can achieve the mathematical perfection required for complete symmetry. The vast majority of mathematical structures are forced to contain asymmetrical elements. These impossibility results help explain why perfect symmetries are never observed in physical systems. The mathematical frameworks that describe natural phenomena are subject to the same limitations that prevent perfect symmetrical structures in pure mathematics. Physics cannot achieve what mathematics proves to be impossible. The connection between mathematical impossibility and quantum mechanics is particularly striking. Heisenberg's uncertainty principle can be understood as a manifestation of mathematical constraints that prevent the simultaneous specification of certain pairs of properties. You cannot know both the position and momentum of a particle with perfect precision because the mathematical framework of quantum mechanics is constructed in a way that makes such knowledge impossible. Similarly, the no-cloning theorem in quantum mechanics proves that perfect copies of quantum states cannot be created. This isn't just a practical limitation of current technology. It's a mathematical impossibility that follows from the linear structure of quantum mechanics. Perfect symmetrical copying of quantum information is forbidden by the mathematical laws that govern quantum systems.